Welcome back to my course Aspects of Biochemical Engineering. In the last lecture, I tried to discuss the different type of reactors, and we have seen that we have different reactors is used both in the chemical and biochemical industries. As for example, we have if you look at the mode of operation, on the basis of mode of operation, it can be have three different type of reactors. One is called batch reactor, another we have head batch reactor, another we have continuous reactor. And then we also come back to the other different type of reactors, like in the continuous reactor we have CSTR, we have plug flow reactor, and I told you that CSTR is very easy to operate, but plug flow is a little bit difficult to operate, because during the flow there should not be any kind of back mixing that take place in the reactor. Radial mixing is permissible, not axial mixing. So that is the problem that we have. And then we discussed different other type of reactors like packed bed reactor, expanded bed reactor, fluidized bed reactor. Also we discussed the bubble column reactor, airlift reactor, and also I showed you what are the how the reactor looks in industrially, that both in the biochemical and chemical processes. Now today I want to discuss very important topic, that is called reactor analysis. Now why the reactor analysis is required? Because to find out the volume of the reactor, because so in the industry, suppose I want to produce a certain amount of product. Suppose I personally work with citric acid industry, and we produce 4 to 5 tons of citric acid per day. Now question comes that for the production of citric acid, what should be the volume of the reactor, how we can calculate. So until unless you have the expertise, you have the knowledge of reactor analysis, you cannot do the analysis. So to this lecture is totally deals with that. Now first let me discuss that that the analysis of the reactor. We have the material balance, we have substrate, we can see the substrate balance and the product balance and energy balance. So three different way we can do that. One is substrate balance, another is product balance, and the energy balance. So that we can do this balance of the equations that we can do. Then if you look at the formula, because we considered basically it is a kind of formula, that what kind of equations we have for the reactor analysis. So we have the input equal to plus generation equal to output plus disappearance plus reaccumulation. Now when you do any kind of reactor analysis, we should always consider that that a one particular component. As for example, suppose I want to produce A to B, am I right? A is the substrate and B is the product, am I right? So if we want to do the analysis, we can do the analysis with respect to substrate. So if we put then rate of substrate input equal to rate of substrate generation, rate of substrate output plus rate of substrate disappearance plus rate of accumulation. This is the equation that we have. Now if you want to do the balance equation, this is kind of balance equation, am I right? And if we write the balance equation with respect to product, how we can write rate of product input plus rate of product generation equal to rate of product output, rate of product disappearance plus rate of product accumulation. Now we can write this balance equation with respect to the energy also. Rate of energy input plus rate of energy generation plus rate of energy equal to rate of energy output plus rate of energy disappearance plus rate of energy accumulation. Now first let me consider the batch reactor. In the batch reactor, we want to apply this same formula in the batch reactor. Now what is batch reactor? Batch reactor is considered unsteady state operation, where the composition of the reactant keep on changing with respect. So what I want to do, that suppose there is a reaction A to product, am I right? So I can write Ca with respect to time. So it is keep on decreasing with respect to time. So at different time, at different time you have different Ca value. Now, if you have the rate equation, what is the rate equation? dCA by dt, am I right, equal to K into Ca, if you consider first order reaction. Now, as your Ca value, K is constant, but as your Ca value changes at different time, this is T1, this is T2, this is T3, this is T4. As the time changes, your Ca value changes. As the Ca value changes, the rate of reaction changes. Since the rate of reaction changes, we call it is a unsteady state operation. So, please so unsteady state means that why is unsteady with respect to the substrate concentration. Substrate concentration is not uniform in the reactor. As the time passes on, substrate concentration keep on changing with respect to time. Now, now if you put this in the previous formula, how we can write that input, I told you in the batch system, we take the material at a time, allow it to react, after the reaction is over you take it out. So, the input and output should be equal to 0, am I right? This should be equal to 0. There is no continuous input, continuous output from the process. So, what is the rate of disappearance? The rate of disappearance is minus R into V. Why minus R into V? What is minus R? Minus R equal to minus dCA by dt. What is dCA? dCA is the mass per unit volume, am I right? So, when you carry out the reaction in the reactor, you have to consider the liquid volume, whole liquid volume you have to consider. So, you have to multiply it by V. Then you consider all the component that carrying out the take part in the reaction. Then this is the what is this? This is the rate of accumulation of A in the system. So, this is the dCA into V into dt. Now, this equation I can write in this form, dt equal to minus dCA into minus R. This we can write. Now, now we can if we want to find out the batch time, how we can do that? How I can do? I can do the integration here. Am I right? I can do the integration 0 to t. So, this is equal to T batch, and this is equal to like this. Now, if you want to calculate this, how you can calculate? So, this is minus R A and this is C A, and suppose the correlation is like this, then suppose this is equal to C A 0 and this is equal to C A. So, area under this curve is equal to T batch. We can easily calculate the batch time like this. Now, I can here let me point out one thing. When you consider any kind of batch process, we should remember that the batch process has particular one drawback. What is the drawback? After the batch is over, you have to take the material out, and after taking the material you have to clean the vessel, then again you have to refill the vessel. It required some time, and this time we call it downtime. This what do you call it? Downtime. So, what is the T total in a batch process? Total time equal to T batch plus T downtime. Am I right? This is how we can get the total time required for the batch process. Now, this is exactly what I have done previously. This is how we can find out, and if your correlation is like this, that we can find out this is C A 0 to C A, and I told you C A equal to what? C A 0 into 1 minus X A. So, with respect to X A also you can do that. The X A will be 0 to X. But one we should understand that when we have the correlation between minus R A by C A, that this correlation, this is equal to C A 0. This is C A, am I right? But when you draw this correlation with respect to X, then you start 0 from here. The same type of correlation will be like this. Now, let me talk about this continuous start time reactor, and I told you continuous start-tongue reactor is largely operated and is easy to operate. And here it is possible to establish the steady state conditions. What is the steady state condition? Steady state condition means under steady state condition, the concentration of the different component present of the reaction mixture remain constant. So how it is possible? This is possible because, let me explain that. Suppose this is a CH am I right? So you operate a particular flow rate, particular substrate concentration. When you run this process, so you take out the materials time to time. This is same flow rate you maintain here. So this is Ca. So initially, when you operate it, you will find Ca value might be changing like this. And time will come, it is constant. When it is constant, we call it steady state, because when this substrate concentration is remain unaltered, then we call it is steady state. Okay. So your material balance is input equal to output, the same that we have as we have done before. Input equal to output, disappearance plus accumulation. Now, how we can analyze the reactor? This is, if you consider here, let us assume this is Fa. Fa is here. Here Fa is the moles of A per unit time. You are feeding in the reactor. Now, how you can write Fa0? Fa0 is equal to nothing but what you can write F into Ca0. What is Ca0? F is the flow rate, volume per unit time, and this is Ca is the moles of A per unit volume. Am I right? This volume will cancel, so it will be moles of A per unit time. So we can write that Fa equal to Fa0 into 1 minus Xa. Now Ca equal to what? Ca equal to Ca0 minus 1 minus Xa. So similarly, we can write that Fa the molar output flow rate here will be equal to Fa0 into this. So this equation, what we can write, that Fa is the input and Fa0, we don't have any generation, because we are this A is the substrate, am I right? And it is producing product. So there is the equation is that rate of input plus rate of degeneration is the rate of output plus rate of disappearance plus rate of accumulation. Now under steady state condition, what is steady state condition? When I told you, when the substrate concentration will be uniform, and this is possible when rate of accumulation is 0. When rate of accumulation is 0, equal to 0, then and only then that your substrate concentration will be uniform. So what will be basic equation? Rate of input equal to rate of output plus rate of disappearance. This is the rate of disappearance. So if you solve this equation, we will get the V, that is V by Fa0. Am I right? Into Xa by this. We can write this. If it's simple equation, if you solve this equation, this Fa0 will cancel, and Fa0, if it is cancelled, then it's minus Fa0 into Xa, minus Fa0 in Xa. You can take it this side, Fa0 into Xa equal to the minus Ra into V. Now you can write V by Fa0 equal to Xa into this. We can easily write it here. Now once we have done this, then now if you look at previous equation, we have seen the previous equation like this. 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 We have seen the previous equ this equation we get in the continuous start tank reactor. Am I right? Now, now this equation how we can write? This is V by F. Now V, I can write it here. That is what is V, and what is Fa0? I told you this is Ca0 into F. Am I right? This is Ca0 into F equal to Xa into minus Ra. Now, this is this is V by F equal to what? Equal to Ca0 into Xa by minus Ra. Can I write? If we can write like this, now what I told you is the Ca equal to Ca0 into 1 minus Xa. The dCa will be equal to what? Minus Ca0 into dXa. Now here you see that this is the Xa that we have, and this minus Ra that you get here, that is that you can then what is this value? This is nothing but what you call space time. This is what is the unit? This is volume. This is volume per unit time. So this is called V by F. V by F we call it space time for the CSTR. Now this is equal to how we express tau CSTR. This is exactly we have done in the subsequent slide. This tau CSTR equal to V by F Ca0, V by Fa0, the Ca0 into Xa. Then what is the Ca0 into Xa? It is Ca0 into, because I told you this is Xa. Xa is equal to what? Ca0 fraction of A that is converted into Ca0. Am I right? So if it is like this, so this is the so Ca0 equal to Ca0 minus Xa, that Ca0 into Xa equal to Ca0 into Ca. So what we have written here, and this is like this. Now let me take the previous equation, BPS plot minus Ra versus, suppose we have Ca. So we have this kind of plots. Now suppose we want to convert Ca0 to Ca. So if you here the area under this curve is equal to tau CSTR, because this is a rectangle, because at Ca what is the rate of reaction is this one, and at a Ca0 it is this one. So this is the concentration difference, the rate of reaction. You multiply it, you will get the tau CSTR. This is how you can find out tau CSTR. Now this is exactly what they have mentioned here, that it has been, you can see that how the area under this curve will be equal to tau, this is equal to tau CSTR. This we can calculate, and it is very simple. If you know the rate of reaction, tau CSTR equal to Ca0 minus Ca minus Ra. So if you know Ra, if you know Ca0, we can easily find out that what is the tau CSTR. Now this is equal to tau CSTR is equal to what? This is equal to V by F. Now if you know the flow rate, though you can easily find out the volume of the reactor. So that is exactly I was saying that this reactor analysis, if you can do, you can find out the volume of the reactor in any kind of production processes. Now let me discuss another reactor, or continuous reactor, what we call plug flow reactor. Now, what is the plug flow considering the steady state plug flow where the composition of the reactant of the fluid varies along the path. Now, in case what is happening that liquid, this is you can find out this is this is the tubular. I told you basically it is a tubular reactor. The liquid is passing through the tube. Am I right? It is passing like this. Now, when it passes like this, that concentration of Ca keep on changing with respect to time. So, if you make a profile that you find Ca 0, Ca concentration, not Ca 0, Ca concentration keep on changing with respect to distance. Like this, you keep on changing with respect to distance. So, naturally that now here what we can do the analysis of the plug flow reactor, we shall have to assume a differential segment in the particular reactor, the small segment that we can consider in the reactor, and we can do the material analysis across the segment. So, we let us assume the Fa, the moles of A that is entering here, and what is going out, that Fa plus dFa, and the volume of this segment is the dV that we have. So, what you can write material, what is the material analysis we have? Rate of input equal to rate of output, rate of dissipation, accumulation. So, under steady state condition, rate of accumulation is equal to 0. This has been mentioned. So, what is the rate of input? Fa across the differential segment. What I told you, this is the tubular reactor, and we assume a differential segment here. Am I right? So, it is coming Fa and going out what? Fa plus dFa. And what is the volume of the segment? Volume of the segment is dV that we have. Now, if you have Fa, so Fa is the input and Fa plus dFa is the output. Am I right? This is the output. And what is the rate of reaction? Minus Ra into dV. So, this I can write that Fa will cancel. Now, what is Fa I can write like this, Fa equal to Fa0 1 minus Xa. That is exactly what he has written there, and this is equal to minus Ra into dV. Now, this we can write that this Fa0 into dXA equal to minus Ra into dV. So, we have this equation. If you look at the previous equation is like this. So, we can write dV. So, what we can write dV by dFA0. Fa0 I can take it here. So, the dXA minus Ra. Am I right? So, that is exactly what he has written here. dV by Fa0, the dA by minus Ra. Am I right? So, this is, so if you do this is the plug flow reactor, and this is the 0 volume, this is the V volume. So, you can integrate from 0 to V volume, and naturally dV will be V, and Fa0 is constant, it will comes out, and this will be like this. Now, what is Fa0? I told you Fa0 is equal to Ca0 into F. Am I right? So, I can write V by F equal to Ca0 into this is Ca0 into this dXA by this, and again I told you that Ca equal to what? Ca equal to Ca0 1 minus Xa. Now, dCa is equal to what? Minus Ca0, Ca0 is constant, dXA. Now, here this is Ca0 and dXA is there. So, we can write this in the form of dXA. So, this will be minus, this is minus, the plus is there. So, it should be minus. So, this equation we can come across this equation. This is equal to again V by F. So, if we find out the tau plug flow reactor, then if we find out the F value, we can find out the volume of the reactor. F is the volumetric flow rate. Now, how you can find out the volumetric flow rate? Let me explain that. Suppose let me first assume suppose this is a CSTR. There is the input and output. Am I right? Then what is the equation that we have? We have equation is that tau CSTR is equal to Ca0 minus Ca minus Ra, and this is equal to V by F. Now, suppose the one industry produce let us assume basis. What is basis? Basis is let us 1 kg of Baker's is production. Baker's is production. Per day. Let us assume that per day or whatever you have per hour. You can say per hour. Whatever you have. Now, if we assume that, then first we shall have to find out the stoichiometry. What is stoichiometry? That how much of substrate gives how much of product. The in case of Baker's is, suppose you have you use the sugar as a raw material, sugar. So 1 gram of sugar produces approximately 0.5 gram of cell. So suppose for 1 kg of Baker's is, how much sugar is required? Sugar is required. This is 1 kg divided by 0.5, this is equal to 2 kg. Am I right? 2 kg you can take. Now, 2 kg, the 1 kg Baker's is you want to produce per hour. That means 2 kg Baker's is required per hour. But provided your conversion is 100%. But usually your conversion cannot be 100%, maybe 95%, 98%. So again you divide by that factor maker, maybe 98%. So this is the exact amount of substrate that is required for your system. Now, if you know what is the initial substrate concentration here, so if you divide by what is the initial substrate concentration, the kg per unit volume. So kg will cancel, volume will go here, that volume per unit time. So volume you can put it here, flow rate you can put it, that is volume per unit time is the flow rate, and this then you can easily find out the volume of the reactor. Similarly, you can do this same thing you can do in case of plug flow reactor. This is how you can find out the volume of the reactor. And here in the plug flow reactor, when you do the correlate that previously you can remember that when we talk about the CSTR, the area under this curve this is like this. This area under this curve we call it, this is tau CSTR. Am I right? But now in case of plug flow reactor, when is the area under this curve is this is called tau plug flow reactor. So obviously, if your any kind of reaction, if you have the correlation between 1 by Ra versus Ca, you have this kind of pattern. I can easily say that tau CSTR will be much less than tau CSTR. So naturally, if the tau CSTR is less, then this is equal to what? V by F. The F is more or less constant in the particular continuous system. So if you want to produce a definite amount of product, so V of the reactor, volume of the reactor, directly proportional with the space time of the plug flow reactor. So as it is decreases, so your volume of the reactor will be less. So we will go for, if the correlation is like this, then we will go for our choice is plug flow reactor. But if we have other type of correlation like this, then if you look at that Ca0 by Ca, the area under this curve, you have tau CSTR, but area under this curve will be tau plug flow reactor. Now this is much less than tau plug flow reactor. So, in that particular if you have correlation like this minus R A by the C A 0, then we will go for our choice will be tau CSTR. Now, I have one observation here because I want to share with you. Now, what is this situation? You try to think over that. As the substrate concentration decreases, 1 by R A increases. 1 by R A increases means that R A decreases. As the you imagine the situation in the reactor, when the substrate decreases, substrate concentration decreases, rate of reaction also decreases. Why it happens? It only happens when there is a product formation. So, this kind of correlation is valid when there is a product inhibition in the system. This is product inhibition, am I right? So, in case of product inhibition, we go for our choice is plug flow reactor. Now, of course, since I told you the plug flow reactor is very difficult to operate, am I right? Now, how is it possible? Question comes: is it possible to replace the plug flow reactor by CSTR? Answer is yes. How it can be done? Now, here if you look at here, if we put the multiple plug CSTR like this, the multiple CSTR, what will be the area of the CSTR is like this. So, 1, 2, 3, 4, 5, 6. So, if you consider multiple CSTR in series, then you will find tau plug flow reactor is almost equal to, not exactly equal to, tau CSTR. If you have multiple CSTR in series, which can be easily operated. Now, here I have given an example. Suppose how we select the reactor. Suppose there is a reaction A to B and you have correlation 1 by R A versus C A is like this. So, I have identified two different zones, this zone and this zone. Now, here you clearly you can find out here area under this curve, this will be what? Tau CSTR, am I right? This is tau CSTR, and so we'll, but here the total area here will be tau plug flow reactor. So, C A 0 to C A dash, with that our tau CSTR will be much less than tau plug flow reactor. So, we will go for our preference should be tau CSTR. Now, here situation will be different. C A dash to C A, the area under this curve will be tau CSTR, and this is this area under this head, this will be tau plug flow reactor. So, this is much less as compared to tau CSTR. So, we will go for plug flow reactor. So, what I have written here, that in that particular what is our choice? First C A 0 should be passed through the CSTR, so that it converted to C A dash, and then it passed through the plug flow reactor, you will go to C A. So, what I have written here, to minimize the space time, the following strategy is to be maintained: the CSTR followed by plug flow reactor, because the space time is equal to V by F. If the time overall space time is reduced in the particular reaction, then volume of the reactor will be very less, and if the volume of the reactor is less, our cost involvement of the process is less. This is how we can select the reactor. Now, in this particular lecture, I try to discuss that how we can find the batch time of a batch process, and how you can find. I told you batch process is an example of the unsteady state reactor, and if you wanted to have the steady state reaction, only it is possible in the continuous reactor. But one thing I want to highlight, that steady state conditions will be prevail at an infinite time. No, instantaneously it cannot be done. You have to run it for quite some time until and unless is attained the steady state. And so we try to analyze the CSTR, we try to analyze the plug flow reactor, and we have seen that plug flow reactor is suitable for the product inhibition reaction. And but plug flow reactor can be replaced by the multiple CSTR, because I showed you that how it can be multiplied, and finally I showed you that what is the strategy we should have for selecting the different reactor in a particular reactions. Thank you very much.